Yeah, welcome everybody to the row this week. So I'm very happy to introduce two speakers, or not introduce, but we have two speakers. I will first introduce our first speaker, which is Donato. He's a PhD student at the University of Amsterdam. Small disclaimer, he's in the same group like me. And he's working on the intersection of optimization and machine learning. Currently, he's on a research stay at the MIT. So he's talking from Boston. And yeah, he's one of the main developers of Optical, which is software for an algorithm for optimization with constraint learning. Yeah, but today he will talk about robust counterfactual. So please, Donato.
Yeah, thanks, Yanis. I will share the screen. Can you see it?
Yes, we can see it.
Okay, perfect. Okay, we'll move this up. Okay, perfect. So thanks for introducing me. As you said, today I will talk about robust counterfactuals. So counterfactual explanations via robust optimization. This is a joint work with Yannis, Tobias Rob Guttart, Ilker Birbil, and Dick Den Ertog. Now, I guess all of you know about artificial intelligence and how artificial intelligence is affecting society nowadays. There are a countless number of applications and paper in research that show how artificial intelligence is having a positive impact on the society. And some of them are like, for example, the new system from DeepMind called AlphaFold, where Google is showing how this predictive model based on deep learning is able to compete and outperform state-of-the-art methods to predict how protein unfold on themselves. And there are other applications, for example, how AI can be used to handle severe weather conditions, or how artificial intelligence can use to predict skin cancer, reduce waste of food, and so on. But now there's a question that comes almost naturally, which is how much can we trust these predictive models? So I think we all agree that artificial intelligence is everywhere nowadays, but can we trust them? There's a famous example from a Danish entrepreneur called David Hansen, and he, together with his wife, applied for Apple Card, and then he's claiming in a tweet that the program is sexist, and this is because the wife got 20 times less the credit limits that he got. He tried to talk to some representative from Apple, and what they said is, well, we are not discriminating, it's just the algorithm. So, well, the funny thing is that it happened also to Steve Wozniak and his wife. And Steve is one of the co-founders of Apple. And in this case, the wife got 10 times less the credit limits that he got. So if we want to trust artificial intelligence, we need to come up with some kind of explanations. So we have these predictive models. How can we explain the predictive model? A nice definition that I like is from Marcus et al. And they say an artificial intelligence system is explainable if the model is intrinsically interpretable, or if not, we are able to complement it with an interpretable explanation. So which means that we have two scenarios. The first one on the left is where we have model-based explanations. These are predictive models that are intrinsically interpretable. So like linear regression, decision trees, nearest neighbor, and so on. But while these models are interpretable, sometimes they do not lead to high performances in terms of prediction. And so we need to rely on so-called black box, difficult models that are difficult to interpret. But in this case, we can rely on post hoc explanations, which means that we have our black box, and then we try to come up with some explanations, which might be model-based explanations. It can be done training linear models or interpretable models on local parts of the black box. Or we can use attribution-based explanations, which means that we have some features importance methods. And finally, the example-based explanations, also known as counterfactual explanations. And this is the main topic of this talk. So let me give you a more formal definition of a counterfactual explanation. So we start from the idea that we have data, we train our predictive model. In this case, H is the predictive model. Let me see if I can use, what's the point? Yeah, so H is a predictive model. We assume it's a classifier, but this can be generalized to regression models. So H takes in input an n-dimensional vector, and the output is binary, will be either 0 or 1. So if we train our predictive model and we give in input what we will call factual point, x hat, we'll get an output, which is y hat, and it will be either 0 or 1. Now, the counterfactual will be the closest point to x hat, such that we have a flip in the prediction. So imagine the prediction for x hat is 0. We would like to find the closest point to x hat that has a prediction of 1. Okay. Now, there are different ways to tackle the problem. One way is to write an optimization model where we minimize the distance between x. This x is the counterfactual and is also decision variable, and x hat, which is now a parameter. The predictive model H is fixed, and we force the output to be equal to the desired outcome YCF. And there are also on this topic many papers since 2018. It's a very active research field. Now, I just mentioned 3 of them, but there are really a bunch of papers about counterfactual explanations. And let me give you an example to make it even clearer. So we have a predictive model that is predicting if a person is risky or not for a bank in order to be granted a loan. So we train the model on some historical data, and then we have a new person. Imagine you go to the bank, you are 27 years old, you have a yearly salary of 42,000 euros and an account balance of 10,000 euros. You apply for the loan, and the loan application gets rejected. Now, the counterfactual is the closest point to us, which will flip the prediction. So the bank can say, okay, now the loan application got rejected, but if you come back here with a salary that is 3,000 euros higher, which means that we go from 42,000 to 45,000, then your application would be granted. So your loan will be granted. But okay, fine, we can do it. But the question is, what about the account balance? What if we change in the meanwhile account balance and it's going down of 100 euros or it's going up of 100 euros? Are we still sure that the loan will be granted? Well, that's the goal of our project, was to find counterfactual explanations that remain valid also after small changes in the features, okay? And mathematically, it means that we have a counterfactual XCE, which is feasible also for small perturbations, and the perturbations are in an uncertainty set S. So if we look at the pictures here, we have 3 types of uncertainty set: the L2 norm, the L infinity norm, and the L1 norm. We have the counterfactual X, which is the center of each ball, and then we say, okay, X has to be a feasible counterfactual, but also small perturbation in the uncertainty set must be also feasible. Okay, so if we look at this picture, imagine we have a predictive model that is saying, okay, if we are in the red region, it means that the loan application will be successful. Otherwise, if we are in the white region, the loan application is not successful and you will get rejected. The factual instance is the yellow point, and the yellow point is in the white region. And so according to the predictive model, the application should be rejected, but the counterfactual is, the robust counterfactual is the closest box to the yellow point, such that every point in the box is contained in the red region, okay? So please, if you have questions, feel free to interrupt me. Now, there's been some literature, some research in the field, especially in the last year. Although all the papers about robust counterfactual focus on gradient-based heuristics with probabilistic guarantees on the robustness, and they are not able to deal with decision trees. So they can only do it for predictive models for which we can calculate the gradient. So this is not applicable to decision trees, and what we can have is what we see in the pictures on the right. So for example, here, not every point in the uncertainty set is resulting in a flip in the prediction. As you can see, part of the points are overlapping the red region, or like in the picture on the right, this is not the closest ball to the counterfactual. And we would like to have the closest one because, of course, we claim that the closer, the better in terms of how easy it is for the user to achieve it. We can ask the user to bring the salary to 100,000 euros, but of course, this might be doable for, like, you will get the loan application accepted, but it's also very difficult to achieve it. So we want to keep it very close to the current situation, which is the black dot you see here. Okay, so the method we developed had two specific goals. The first one was to prove, to guarantee full robustness in the entire uncertainty set. And the second point is that we also like to develop a model that is applicable to decision trees and ensembles of trees, like random forest, gradient boosting, and so on. This is because for specific data set, trees have been proved to be very good in terms of performance and also explainable whenever they are not too deep. And same for ensembles of trees. Now, the problem that we have to solve is the following one. So given a factual instance X hat, a robust counterfactual explanation can be obtained solving problem 1. Problem 1, we minimize the distance from the factual point, and we have a constraint that the predictive model has to return something that we desire, so it has to be greater than a threshold tau, and tau can be chosen according to the desired outcome. And this has to be true for every perturbation of X. So X plus S with S in the uncertainty set script S. Okay, so for every perturbation, we would like to be feasible. We did it for linear regression, we did it for decision trees and ensembles of trees, and we did it also for neural networks with the ReLU activation function. Of course, it's not always straightforward. There are some difficulties. The first one is that problem 1 has an infinitely many constraints. We know from the robust literature is that sometimes we can use the duality trick to obtain a finite number of constraints, but this is not always possible. For some of the predictive models, it's not possible anymore. That's why we came up with an iterative approach. Okay, the iterative approach is the following one. We have two main ingredients. We have the master problem and the adversarial problem. Let's first focus on the master problem. The problem itself is extremely similar to what we have here, so to problem 1. The only difference is that while we have a constraint for every point in the uncertainty set in problem 1, here we restrict our uncertainty region to some scenarios, so to that which is a finite number of scenarios in S. Of course, solving this problem will provide a lower bound on the optimal value because the number of constraints is less than what we have here in problem 1. So we can solve the master problem. We obtain a solution that we call X star, and then we can move to the adversarial problem. So this adversarial problem finds a new scenario in the uncertainty set S, which maximally violates the constraint for current solution X star that we obtained from the master problem. Okay, so what we have is we maximize the violation of constraint in the predictive model outcome, and we have a constraint on S, which is now the decision variable, and S is constrained to be in the uncertainty set. So the solution X star that we obtain from the master problem is cut off if the optimal objective value is greater than 0. So if we have at the optimal objective value something greater than 0, it means that we have a new scenario to add in Z. Otherwise, we can terminate the iterative approach. I'll show you more like graphic intuition of the iterative approach. So we have the master problem and the adversarial problem. The master problem takes an input, the initial set of scenarios Z, and the functional instance X hat. We solve the master problem and we get the optimal solution, which is X star. Now, X star will be an input of the adversarial problem, which takes as input also the uncertainty set S, the original uncertainty set. We solve this problem, we obtain an objective value and a new scenario. We check that the objective value is greater than 0. If this is the case, we continue with the next iteration, which means that we include the new scenario S in Z, and we solve again the master problem. We will stop when the objective function is not greater than 0. In that case, we can say, okay, now the X star is our optimal counterfactual explanations, is proven to be robust in every point in the uncertainty set S, although we didn't use the full uncertainty set, but just some scenarios. And then we can also prove that this is the closest box, closest, let's say, ball to the factual instance. Now here in this GIF, we have the number of iterations. Let's say we start from iteration 1. The factual instance is the yellow dot. So we look for solutions, and this will stop only when the adversarial problem objective function will be greater than 0. So as you can see at iteration 11, it will stop and it will say, okay, this is the optimal robust, this one, the optimal robust counterfactual. So we went one step further, we proved convergence of our algorithm. And the convergence proof is based on the Mutapcic and Boyd theorem, where they claim that if X is bounded and H, the predictive model, is Lipschitz continuous, then our algorithm will terminate after a finite number of steps. So the key point here is that the predictive model has to be Lipschitz continuous. Now, the logistic regression is a Lipschitz continuous function. Neural networks with a real optimization function is also Lipschitz continuous, because a composition of Lipschitz continuous functions is also Lipschitz continuous. The problem comes with decision trees, which are not even continuous. So what we did for decision trees is we changed a little bit the decision tree without affecting the prediction of them, but making sure that they are Lipschitz continuous. Now, for the sake of the presentation, I don't have time to dive into it, but if you're interested, we have, yeah, you can send me an email or read the paper. So for decision tree, so we have our optimal approach. Once we reformulate the decision tree, we can use the iterative approach, having a proof of convergence. Or another way to deal with decision trees using a heuristic approach. So the optimal approach is fast whenever we deal with small decision trees, or like not with ensembles of decision trees. But when the decision tree is extremely deep, or we have hundreds of decision trees for the random forest or gradient boosting, the iterative approach might become slower, because the number of constraints that we add to the master problem is increasing at each iteration. That's why we came up with an heuristic approach. And the heuristic approach is extremely fast, because we constrained the uncertainty region to be fully contained in one leaf. So we have a picture here. The optimal approach, as you can see, the factual instance is in the yellow region, which is classified as 0.8. So we want to flip the prediction. It means that we want to obtain something that is less than 0.5 to go from prediction 1 to prediction 0, let's imagine. Okay, now on the left, our uncertainty box, our robust counterfactual is contained in 3 different leaves, the yellow, the blue, and the violet one. All of them predict something that is less than 0.5. It is fine. It's overlapping multiple leaves. This is the optimal in terms of distance to the factual instance. On the other hand, if we use a heuristic approach, we constrain the box to be fully contained in a leaf. So the closest box would be the one we see here. It's contained in the red leaf of the decision tree. Fine, it's extremely fast, but this is not optimal in terms of objective value. Going to the results. So we run some results on 3 different data sets. The first one is the banknote authentication. It contains data points, 4-dimensional data points. The second data set is the diabetes data set with samples in n dimensions. And the last one has samples in 34 dimensions. Okay, so what you can see, the first column is the model, the predictive model that we trained. We tried with linear regression, decision tree, random forest, gradient boosting, and neural networks. And for each model, we tried different complexities. So we started, for example, the decision tree with a max depth of 3, and we went up to max depth of 10. In the case of random forest, we tried, so we fixed the depth to 3, and we increased the number of Bayes estimators in the random forest Bayes learners decision trees from 5 to 100. We did the same for gradient boosting, and for neural networks, we changed the number of layers and the number of nodes per layer. Like in the first case, we have 1 layer with 1 layer of 10 nodes. In the second case, we have 3 layers of 10 nodes each. Here we have the computation time in second with the standard error between brackets and the number of iteration of the iterative approach. So this is an average over 20 instances, and uncertainty set that we use is a L-infinity norm with a radius of 0.01. Now the data, we scale the data, which means that the counterfactual has a box that can change of, let's say, up to 2% in this case. We tried also other experiments with rho equal to 0.05, which means that we can change of up to 10% each feature. Now, what's interesting is that most of them terminate within the time limit that we set, which was 500 seconds. Of course, the computation time increases with the complexity of the predictive model, but doesn't change too much with the number of features of the data set. As you can see here, it's more or less stable. The most difficult random forest takes at most, on average, 200 seconds, and this is not changing too much, increasing the number of features. Something that we can also look at is the number of early stops. So whenever we hit the time limit, we can stop the algorithm. We stop the algorithm. And the nice thing is that even if we stop it, we can still give some guarantees about the robustness. So we have a counterfactual that is not fully robust in the uncertainty set with radius 0.01, but we can find the smaller radius for which the counterfactual is robust. Okay, so on average, here it's 0.009, which means that we lose a 10% in terms of radius, but this is still a feasible counterfactual in the ball with radius 0.009. Okay, and yeah. So to conclude, there is some future work that we plan to work on. First of all, we like to speed up the calculations of the master problem, which is the part that takes most of the time to solve. And the way to do it is using different formulations for the predictive models. In the literature, there are different formulations for neural networks. There are different formulations for decision trees, more or less efficient. So we would like to try with different formulations. And also we would like to extend our formulation to include categorical features. If you're interested, you can get in touch using this email or checking the GitHub page where we release the code of our approach. There's a paper, it's called Finding Regions of Counterfactual Explanations by a Robust Optimization, and it's available on arXiv at the moment. So I think that's it. We have maybe some minutes for questions.
Yeah, thank you very much, Donato. Having a look at the time, maybe one or two quick questions. Anyone, please feel free to ask.